Kfir, and she'll talk to us about the boundary of hyperbolic free-by-cyclic groups.
Thank you very much. It's really nice to be here. I love being in England. I love the way you talk. And the bar testers aren't so bad either. Okay, so this, I was lucky that wasn't recorded. All right, so this is joint work with Arnaud Hilion and Emily Stark. Okay, and many of you are interested in free-by-cyclic groups, so that's nice. And those of you who aren't, I'll try to make a case for them. So, so like we heard in David's talk, I'm going to be interested in phi and outer automorphism. So an element of the group odd of Fn modded by the inner automorphism group. And suppose that phi is an automorphism of Fn in the class of phi. So we're interested in free-by-cyclic groups. Let me remind you what they are. I'm going to denote it by Fn by phi. I guess this is just notation. This is defined to be Fn, the H&N extension of Fn by phi. And this has the following presentation. Just like the we told us, t you conjugate x by t, and you get phi of x. Okay, so these are the groups that we're interested in, and there's a nice correspondence between G and properties of G and properties of phi. So I'm going to make a table. I think I should have used the other board. Okay, so let me tell you a property of phi. Phi is called atoroidal if for any conjugacy class in Fn, phi of W is not the same conjugacy class. There's no fixed conjugacy class. So phi of W is not equal to the conjugacy class of W for all W in Fn. Okay, and in this case, Peter Brinkmann showed that G is Gromov hyperbolic. Okay, so it has a boundary. Okay, and boundaries of groups, they are compact and metrizable. Okay, so we know this about the boundary. What else? Suppose I want to know if the boundary is connected. Okay. I guess this is the same as being one-ended. Okay, and then Stallings tells us that if the group doesn't, it's connected once I know that the group doesn't split over a virtually finite subgroup. So G doesn't split over a virtually finite subgroup. And Kapovich and Kleiner basically have an argument to show that in this case, it never splits over a virtually finite subgroup. So we're in this case, and all of these boundaries are connected.
What do you mean virtually finite?
Finite, yeah. I'm obviously thinking of the cyclic case. Okay, so that's nice about the boundary. What else do we know? Okay, so I guess we can all find a contractible space, a contractible 2 complex on which G acts. So the cohomological dimension of G is 2, and Bestvina and Mess then show that the topological dimension of the boundary is 1. 1 less the cohomological dimension. Okay, so that's nice. And then it's also locally connected and Brian told me, so I have a bunch of names to write here. Bowditch, Swarup, and I guess they were also building on work of Bestvina and Mess and Levitt and others, but I'll write these. And then what about local cut points? So Brian Bowditch said that a group has a local cut point in its boundary if and only if G splits over a virtually cyclic subgroup, a virtually infinite cyclic subgroup. Okay, this happens, so if there are, no local cut points, then G doesn't split over a virtually Z subgroup unless it's a Schwartz triangle group and then the boundary is the circle, but we're not in that case. And G splits over Z exactly in the following case. It corresponds to phi preserves a free splitting, preserves. So if it doesn't preserve a free splitting, then it doesn't split over Z, and then there are no local cut points, so I should add doesn't. Okay, and in order to get this, we can assume that phi has, let me write this like this. No free factor of Fn is preserved by a power of phi. Okay, so this is a very important property. It sort of says that the phi is irreducible. But there's like a war in out of Fn about how to call this property, and there's like a fully irreducible camp, and there's the IWIP camp, and I'm kind of sleeping with the enemy here because I'm from the fully irreducible camp and Arnaud is from the IWIP camp. So I propose peace. Let's call this fully IWIP. Okay. I don't know if I'll remember to call it that. I'll probably just revert to fully irreducible. But
would it be fully irreducible with fully irreducible powers?
that's also an option. But I'm at the board here, so I get to pick. All right, so okay. So we have this. So we know all these things. And once we know that phi is atoroidal and phi is fully IWIP, then we know that the boundary satisfies all these things. And then you can recall characterizations of spaces that satisfy these things. Okay, so if X is metrizable, connected, locally connected, with dimension equal to 1 and no local cut points, then there are basically two options. Either X is planar, and then X is homeomorphic to the Sierpinski carpet. Okay, so what is the Sierpinski carpet? It's a fractal. You take a square, and then you remove the middle square, and then you have 8 other squares like this, and you perform the same operation, removing the middle squares. And like Ian likes to say, it could go on forever. Or I don't know, I'm attributing this to you. Okay, so in the limit, you get a Sierpinski carpet. Okay, and the other option, suppose that no open set is planar, then X is homeomorphic to the Menger curve. It's just a 3-dimensional version of this. You take a 3 cube and you punch a finger through the middle, through every face, and then you continue doing this to any little subcube. Okay. So I guess Kapovich and Kleiner noticed this, and then they said, okay, so if a group has a one-dimensional boundary, not necessarily this free-by-cyclic group, but any one-dimensional boundary, then the only options are that it's the boundary is the Sierpinski carpet, the Menger curve, or the circle where it's a Schwarz triangle group. Okay, and they also had an application for this. They said also that in this case, in the free-by-cyclic case, because they know that there's no splittings and all of these things happen, they can rule out the Sierpinski carpet. But they had a really, I shouldn't say strange, but it was like a roundabout argument for this. They characterized which group had a Sierpinski carpet boundary. They said that they have to be Poincare duality groups of some type, and they showed that the Euler characteristic is negative, and the Euler characteristic of this group is obviously 0, so it can't be the Sierpinski carpet, so it has to be the Menger curve. Okay, so now I come to our theorem. We wanted to see this more directly, so we prove that if phi is atoroidal, then there exists an embedding of K33 in the bound. Okay, and so it can't be the Sierpinski carpet, so it has to be. So in the case, if phi is atoroidal and fully irreducible, then we know that it has to be the Menger curve. But this is slightly more general, and I think it's we have we wanted to get a good understanding of the boundary. We don't have a good understanding, but we have some understanding of what the boundary looks like. Okay, so okay. So I should say the converse holds as well. I guess I wrote that in the abstract. If phi is toroidal but still fully irreducible. So I have to say, I mean, these two conditions, they're sort of related to each other. They're sort of irreducibility conditions, but one doesn't apply the other. But if we suppose this, if it's toroidal but fully irreducible, then phi is induced by a pseudo-Anosov on a surface with a puncture, okay, which fundamental group is free. And then for those types of groups, I could still do this H and N. And those are cat-0 groups with isolated flats, so they have boundary, and it's the Sierpinski carpet. Okay? So one of our goals was to understand how we can see this difference in the two cases. Okay, so let's restrict our attention to the fully irreducible case. I mean, the theorem is for atoroidal, but I'm going to talk about the fully Iwick.
Yeah, can I ask you a question? So
Yes.
how come the argument with the characteristic fail in that case?
It doesn't fail. Which fail?
So, I mean, these guys obviously have only characteristic 0.
They're not Gromov hyperbolic.
That's the difference, I see. Okay.
Yeah, but it's sort of not clear what goes wrong, right? So we'll show how you can see it. Okay, so if it's fully irreducible, now I'll define outer space. Okay, so let's look at outer space. It was defined by Kohler and Volkmann. It's the space of trees and actions on it. Okay, where T is a metric simplicial tree, and rho is an action of Fn on the tree, and we mod out by equivariant homothetes. Okay, and outer space was compactified by, I guess, Kohler and Morgan, and then Cohen and Lustig identified what the compactification was, and I guess I should also say Bispina Fein. If you want to compactify, you no longer have that T as a simplicial tree. T is just a metric R tree. So there could be lots of branching, and didn't write free here, free simplicial, and the action is not necessarily free or simplicial. It's what they call rho is very small, and I won't get into what this is. We still have the equivalence relation, but it sits inside this compactification. Okay, and out of n acts on this, so the action on CVN, it's just you take T rho and you twist rho by phi, so you precompose rho. Okay, so this is the action. Maybe it's a right action. Some people care. I don't at this point. Okay, and if phi is fully irreducible, then it acts by north-south dynamics. Okay, so we have an attractor and a repeller, and those are going to be important for us. So I'll denote T plus the attractor and T minus the repeller. And these trees are really, they're not in CVN, they're really on the boundary of CVN. So properties, the Fn orbits of T plus and T minus are dense. And in fact, they're indecomposable. So T plus minus are indecomposable. For those of you who don't know what that is, like me a year ago, it just says that they have this dynamics, which is, they're highly mixing in terms of the dynamics. But, dense orbit is a good picture to have in your head. Okay, and then we also have another tool that we're going to use, which is the Q map. So there exists a map from the boundary of Fn to any T with dense orbits. So I guess, if I apply this to T plus or T minus, I'll write Q plus and Q minus. So this is by Levitt and Lustig. If you put the right topology on the tree T, I should say, for any T with dense orbits, you have sort of a map to here, only you have to complete it. These trees are not necessarily complete. There's points that don't belong to T, which are a finite distance. So we complete it, and then we take the Gromov boundary as well. Okay, so I'll call this thing T hat. Okay, and there's a map from the boundary of Fn to T hat, which is equivariant okay, and continuous if you put the right topology. Okay, and then I want to define a lamination corresponding to this Q. So what's a lamination? L of T. It's just points on the boundary which map to the same point in T hat. Okay, so I'll take X and Y in the double boundary. So meaning that I don't take X to be equal to Y, such that Q of X equals Q of Y. Okay? And this is a subset of the double boundary, and it's closed, Fn invariant, flip invariant. So meaning that you could switch X and Y, non-empty. So this is basically the definition of a lamination in the boundary of Fn, closed Fn invariant, flip invariant, non-empty subsets. Okay, so using this, I get Q plus, Q minus, L plus, and L minus for these attractor and repeller. Okay, so I kind of want to see this Q map. So I'll imagine the boundary of Fn as the boundary of some simplicial tree. Can everybody see here? Okay, so this is boundary of S. This is the simplicial tree. Just imagine the Cayley graph. Okay, and then I have T plus and T minus. Maybe I'll switch this to, I want everybody to see. Can everybody see here? This is going to be important. Okay, oh, okay. T minus, T plus. Okay, and I have, what are these guys? They're pairs of points. I can think of them as a geodesic, X and Y. And this is in the lamination for T minus if it goes just to one point. And in fact, these points are going to go to points sort of in the interior of, I should have put hats here, right? So this is the Q plus map, and this is the Q minus hat map. So this is the lamination for T plus. For T minus, in T plus, it'll actually map isometrically to a line here. Okay, and in T minus, and the other picture is like this, maybe I'll have something looking like this, you know, X prime, Y prime, and those will map to some point here, and it would still map isometrically here. Okay, so this is in the lamination of T plus, and this is in the lamination of T minus. Okay. Okay, so I'll erase this. Okay, so Mitra proves that for the injection of Fn into G, I have an extension of that to the boundary, to a map from the boundary to the boundary. So for this map, there exists a continuous extension. It's called the Cannon-Thurston map So I'll denote it ICT from the boundary of Fn to the boundary of G. Okay, and this map factors through the Q's. So this is not part of what Mahan proved. This is actually by Kapovich and Lustig. It's not the same Kapovich as Kapovich and Kleiner theorem. This is Ilya, and that was Misha. Okay, so Kapovich and Lustig show that you can factor I through these maps, through the Q maps. So if you look at this map, this is the Cannon-Thurston map, but it factors through Q, so I'll denote this by R plus, and the same is true for T minus. Okay. Okay, so why is this important? What's nice about this R plus and this R minus is I sort of understand them very well. Okay, R plus is injective on T hat minus its boundary. So things that are identified, okay, so I basically have, what it's basically telling me is that I have this picture in the boundary of G, only, you know, point on the boundary of T plus can get identified. Okay. I should say this is onto, and they do get identified. Okay, and the same goes for T minus. But also, if I look at the interior of these guys, the images are disjoint. Okay, so if I want to find a K33, I could find it using these pictures. Okay, so I'll write those properties. Okay, so R restricted, maybe I should say R plus minus restricted to, I'll call it int of T hat plus minus. It's everything but its Gromov boundary, so including, I guess, points in the completion. This is injective. The images of T plus with, I mean, interior. Maybe I'll use, I don't know. When I don't write hat, I just mean the tree T plus. Okay, R plus T minus, they're disjoint. And also the image of T plus and its boundary are disjoint. Okay, and I also understand when things are identified. So when are things going to be identified in the map? I guess there's a map here to the boundary of G. They're going to be identified if they belong to the lamination of the other guy. Okay, so R plus of some x equals R plus of some y if and only if x is q plus of some point and y is q plus of some other point, such that this is contained in the lamination of T minus. Okay, and vice versa. Okay, so we really understand how this picture glues together. Okay, so now suppose we want to show that there exists an embedding of K33. Okay, but these trees are sort of, I don't know if they're planar, but I think of them as planar. You know, I'm not going to find, not planar, but you know, I'm not going to find loops inside T plus or T minus. They're trees, okay? So I have to sort of see how I can get K33, okay, embedded inside my tree. Okay, so the picture is this. I'll erase what I have in there. Okay. By the way, I should say that these guys are called, it's kind of weird, but this is the lamination for the repeller, and it's called the attracting lamination. Sometimes it's denoted, I guess, L+, and this is the repelling lamination. Sort of like, I guess, historically how they came up. Okay, but what I'm going to do is this. There exists laminations that are singular in the sense that two leaves share a whole ray with each other. Okay, so I can find this. And now suppose I was able to find leaves that traveled along this for a while inside this attracting lamination. Okay, so maybe suppose I was able to find this. Okay, now I'm going to label this. So I'm going to call this point 1. These 3 points, you know, they're endpoints of, these 2 points are endpoints of the same leaf of the attracting lamination. So they'll map to the same point in the boundary. So I'll denote them by 2. And also because of this leaf, these are all going to map to the same point in the boundary. Okay? But these points will map to different points. Okay, so I'll label them 4. Okay? Now, if I look at 2 in here, I mean, this corresponds to a leaf in the lamination. So it'll map to a point 2 inside T minus, and also 3 and 4. And suppose the picture was like this. Let me use a different color. Okay, 3 and 4. And suppose that the convex hull of 2, 3, and 4 looked like this. Then I claim that I can see this K, then this gives me a K33 in the boundary of G. Why? Because, okay, let's look at, I have 1. Oh, I should have labeled the other vertices. I'm going to label this A, this B, and this C. Okay. So this is 1. It's connected to A, B, and C. Right? And then I have 2 is also connected to A, B, and C, and it doesn't intersect the other arcs. Okay, and my problem is with 3 because it's connected to A and B in a nice way. Okay, but I can't really see it connected to C. 3 is really not connected to C in a disjoint way from the other arcs. So what I do is I go here, okay? So I see 3, I go along this arc until I hit 4, and then I go from 4 to C. Okay, so I have this arc that starts with this thing to 4, and then it goes to C. Okay, and these guys are in the interior of T minus, and these guys are in the interior of T plus. Okay, so if I can get this picture of the laminations inside T plus and T minus, I'll be able to map my K33 inside, embedded inside of the boundary of G. Okay, so here's our question. How do we get this picture? Why does this picture arise in the non-geometric case but doesn't arise in the geometric case? Okay, so I wanted to promote the following tool that we used. A lot of people in out of n know how important the weighted graph is, and we defined a directional weighted graph. We hope it'll be useful. Okay, so let's think about the weighted graph. I'll define it here now. Okay, so given a lamination L of T minus and a branch point V in T minus, I'll define the weighted graph in the following way. The weighted graph in T minus of V is, I want to say what the set of edges is, and then vertices, how they're identified, it will be. Has a set of edges corresponding to leaves in the derived lamination of LT minus, that's it, LT minus prime. Okay, what's LT minus prime? So most leaves in this lamination are limits of other leaves, okay? But some are not. I mean, I have these, okay, so it's possible that here, let's look at this leaf, for example, okay? So if I take AB and I apply phi to it, maybe those of you who know can see that this leaf is going to limit to this white leaf that I drew. So it's a limiting leaf. And also this guy is going to be a limiting leaf. But these pair of points also define a leaf of the lamination because of this property that, right, if I have Q maps to the same point as Y and Z maps to the same point as Y, then X and Z are going to be mapped to the same point. But there may not be limiting leaves to these two guys. Okay, so I want to throw them out. This is basically a way to get the Bestvina-Fein-Handel laminations from these laminations that I defined. Okay, so maybe I'll write this as lambda plus Bestvina-Fein-Handel. And maybe I should write that this is attributed to Coubois, Hilion, Reynolds. Okay? But anyway, those are the important guys, the limits. Okay? So I want to look at the limiting guys. Oh, I haven't finished. That Q minus sends to V. Okay? So suppose that, right, so 2 is sent to this point 2, so that's my V. And this leaf is a limiting leaf that maps to V, and this leaf is also a limiting leaf that maps to V. So the weighted graph, the way I've defined it, is going to be just two edges like that. Does that make sense? No? Yes? Okay, basically I take all of the leaves that are important, the limiting leaves, and I look at those which map to my V, and then I identify them on vertices that are, identify them on vertices if they share a vertex. So if I have one edge like this and another edge like C alpha, then they're identified on Xi, so they'll have, they'll share a vertex. Okay. This is a really important tool, the weighted graph. Okay, but we define the directional weighted graph. Okay, so maybe I'll draw a picture. So I have this leaf and this leaf, let's say L1 and L2, and they're limited to by other leaves. Okay. So they're in the weighted graph. Okay. And suppose that this is a picture, say, in the boundary of Fn, or in the double boundary, or in the Cayley graph, and then T plus two guys here, they map to the same point V. Okay, so the weighted graph is going to look like two edges glued together. Okay, but now I'm going to pick a direction, and I'll say that the directional weighted graph contains one of these edges if the sequence that limits to it comes from that direction. Okay, so I'm going to suppose I'll take this sequence, and suppose all of it maps inside this direction of T plus at V. Then this edge will be inside the directional weighted graph. Okay? Okay, and this is basically what we need to get that picture. So, I'll skip writing the definition. Okay, I want to call, okay, did I write this? This type of thing, I want to call it the T plus minus pattern. And we proved proposition that the T plus minus pattern arises if and only if there exists some directional weighted graph with more than one edge. So if I want to find a K33, I need to find a T plus minus pattern. I can look for a directional weighted graph that, that contains more than one edge. So I want to show you what happens in the geometric case. In the geometric case, I always have just one edge. So okay, so in the geometric case, I mean that T minus is the leaf space of a foliation on a surface. Okay? Then what happens? Then locally, I see something like this. This is my foliation. Okay, so I'm switching from lamination to foliation. It doesn't really matter here. Okay, so this is my foliation on the surface. Okay, so and maybe there's other singular leaves here, which I don't care about. I really only care about this local picture. And when I contract leaves, I get sort of this picture. So these leaves in this quadrant are going to give me some sort of direction. Okay, and these other leaves are going to give me maybe other directions. D2, D3, and so on. Okay. Okay, and what about the weighted graph? Okay, so I have this leaf of the lamination, of the foliation, whatever, you know, these pair of points, x and y, and I have a sequence of red leaves that limits to them, okay? And these red leaves, they're all mapped to points in this direction D, okay? So if I'm looking at the weighted graph of this direction, okay, I'll see an edge xy. Okay, But all of the other edges are not going to be in this directional weighted graph. They'll correspond to all of these sequences that limit to xz, for example, are going to come from other directions. So they're not going to be in this weighted graph. Okay, so in the geometric case, I only see one edge in each directional weighted graph. Okay, but then, what time is it? Okay, how many more minutes? 2 minutes? Okay, so let me just say that if one of these trees is not geometric, then I can get a weighted graph with more than one edge. And that was what allowed us to prove the theorem. So we have a lemma saying that if T minus is not geometric, doesn't come from a foliation on a surface, then there exists a weighted graph with more than one edge. Okay, so this allows us, so in the atoroidal case, what happens is it's not geometric. One of the trees doesn't come from a leaf space of a foliation. Okay, so one of the trees is going to satisfy this lemma, and I'll have more than one edge, and then I'll have a T plus minus pattern, and then I'll get a K33. Okay, and I'll just say a word about how we get this. We use the Rips machine, and we show that if it doesn't halt, then you have, three bands intersecting simultaneously, and that for all time, that allows you to get more than one edge in your weighted graph. Okay, so I'll stop here.
I guess it's kind of in the eye of the beholder whether the other argument was more roundabout or your argument
Oh, okay.
more roundabout. So I was wondering whether you had any other kind of direction that you wanted to take this. I mean, it seems very nice to construct.
Well, okay, so a lot of, this was part of just trying to understand these boundaries. So all of them, most of them are the Menger curve. Topologically, they're the same, but they'll have different conformal structures, presumably. I don't know. So this was like a first step to trying to understand really the conformal structure of these guys. So I don't know if that gives you motivation. I think this is more direct because this shows you really where these guys are coming from. Like in their case, you don't see these non-planar regions.
It's more direct. On the other hand, the other one uses Euler characteristic and you use the Rips machine. So in some sense,
yeah, well, we could discuss it, but I sort of feel like I have a better understanding of this than when I started. But what was I going to say? There are other applications that we're working on. They're still work in progress, but if you look at this free-by-cyclic group and you look at its BNS invariant and you look at other points in the BNS invariant, you could ask about what happens there. Do you still see these K33s? And at least in the symmetrized BNS invariant, these K33s persist. So you could get, properties like if one automorphism is parageometric, if one of the trees is geometric and the other one isn't, then you would get that at all points in the BNS invariant are parageometric. In the symmetrized BNS invariant are parageometric. So I don't know.
If there are no more questions, let's thank Yael again.